Now we need to get into the idea of how energy and work are related. We hinted at it in the last slide, but now we're going to really break it down. So I want you to start by remembering that kinetic energy is the energy of movement, right? Which we talked about earlier. Now, we said that work requires energy to happen, right? And so we're going to break down why work is equal to delta K, right? And what what is kinetic energy? So again, energy is something an object or system possesses. It's what allows it to have some sort of change, like we talked about earlier. And so how does work, something that is done on an object, have anything to do with energy, right? Remember that work is equal to force times displacement, right? And we also remember what Newton told us is force is equal to mass times acceleration. And so what you can see is that if you plug it into each other, right, you take F equals ma and you plug it in for this equation right here, what you get is work is equal to mass times acceleration times delta x. Now let's take a closer look, right? Because a times x from our kinematic equations, which we have over here, is equal, see, if you use this kinematic equation right here, right? What you see is that, hey, a of x is equal, if you rearrange the equation, is equal to 1/2 v squared minus v naught squared, right? And now what you can do is you can plug this in over here. And if you're a little bit confused as to how we came up with this, that's honestly beyond the scope of this class as to who sat down and thought of connecting three different concepts together. But we do have the understanding that this is how it was done, and it'll make sense why it works once you are able to derive it this way. Some things that are derived, you don't derive from scratch, right? You have some understanding that you need certain things to come about. But one thing to keep in mind is that these are all equations that we have already learned, right? We're just connecting concepts together. So if you wanted to, you could sit down and think about how all these things are connected, and you could derive this from scratch if you wanted to, right? But for now, we're just going to continue because it's technically out of the scope of this class. So now that we know that a of x is equal to this, again, we're just doing algebra at this point, right? And so we just keep working through the algebra until we get that work is equal to 1/2 mv squared, right? And so what does that really mean, right? I want you to remember something before we explain that point, right? Remember, work is what's being done, right? Energy is what's needed to do work. So that means that changing energy means work, right? Therefore, work is equal to the change in energy right here, this equation. And so this is a phenomenal point to keep in mind. Work is equal to change in energy, right? And what we see here is that kinetic energy has to have some value, right? What we know is that kinetic energy is equal to 1/2. So what you can say, okay, so how do we connect this equation right here to kinetic energy, right? What you want to look at is, what is work equal to? Remember, work is equal to the change in energy. If work is equal to the change in energy, that means change in energy is equal to 1/2 mv squared. Wow, look at that. Now, if the change in energy is equal to 1/2 mv squared, what kind of energy is that, right? Since we're only talking about mechanical systems, what we can say is this change in energy is the change of the mechanical system, right? And so since it's the change of the mechanical system, remember what delta E of the mechanical system is equal to? I'll show you right here. Remember, delta E of the mechanical system, or just E of the mechanical system, is equal to the kinetic energy plus the potential energy, right? And so now let's go back. If this is the case right here, then delta E of a mechanical system is equal to delta K plus delta P. Okay, so remember, the delta E of a mechanical system is equal to the change in kinetic energy plus the change in potential energy, right? And so what does that mean? Well, let's assume that this is zero, right? What happens when the change in a mechanical energy system is zero? What we get is delta KE is equal to negative delta PE, right? Or negative delta KE is equal to with this relationship right here, what we can say is that they aren't necessarily negative, right? They're just opposites of each other. They're the exact same, but they're opposite of each other because of the conservation of energy thing that we just talked about. Is the change in energy is going to be equal to zero of the mechanical system, right? And again, this is only true when it's only conservative forces acting, not non-conservative systems, right? And we won't touch on that just yet. We're going to maintain the idea of conservative systems. Like, conservative forces are the only thing acting upon this system, okay? We're not going to touch on heat and other things like that yet. And so with this relationship right here, what you get is, hey, delta KE is equal to the change in energy. Do you understand why? Because delta E is equal to delta KE plus delta PE, right? And if you remember, delta PE so now what you can say is that work is equal to the change in kinetic energy, which is equal to 1/2 mv squared. That's how you understand that work is equal to kinetic energy. This isn't in all cases, but in mechanical systems, work is equal to kinetic energy, right? It's also equal to potential energy in cases where it has potential energy, right? And we'll touch on that at a later time. But for this specific slide, I wanted to show you why work is equal to delta K, or work is equal to 1/2 mv squared. Okay. Now we're going to do some practice problems where we look at kinetic energy, the equation that we just derived right here. So a shuffleboard player pushes a 0.25 kilogram puck initially at rest such that a constant horizontal force of 6 newtons acts on it through a distance of 0.5 meters, right? What are the kinetic energy and the speed of the puck when the force is removed? How much work would be required to bring the puck to rest? So let's write out what we know so far, right? We know that the distance is going to be 0.5 meters. The initial velocity is 0 meters per second, right? It's at rest. So what is the final velocity? We'll leave it there for now, right? This is just what we know. Now we go back to what else we know. The mass is 0.25 kilograms. The applied force is 6 newtons. And the distance is 0.5 meters. So what can we do with this, right? Kinematics won't work because we don't have enough variables, right? So we will deduce that we can use work, which is force times distance, and we get 3 joules. Now remember, work is equal to delta KE, and delta KE is equal to final kinetic energy minus initial kinetic energy. And so since the initial kinetic energy was 0, because again it was at rest, we can say work is equal to the final kinetic energy. Now kinetic energy is equal to 1/2 mv squared. So when you solve for that, you get your final velocity, which is 4.90 meters per second. Now we have solved part A of the question. Now, how much work would be required to bring the puck to rest? Well, we need the opposite, right? So why? Because if you have kinetic energy moving you forward this way, right, you need something to act exactly, you have to oppose it exactly, right? You have to stop it. And so what you need to do is you need the exact opposite of what you just did. If you added 3 joules into the system, you need to take out 3 joules, right? And so work being done to stop it would have to be the opposite of 3 joules, which is negative 3 joules of energy to stop this puck.